Okay, so this topic here, I'm going to have new functional groups I want to show you. And honestly, the rest of this unit's very similar to what we did yesterday. We're going to talk about new functional groups, talk about some new properties of them. We'll talk about how to make them, if applicable, and like that's really it. How to name them, how to draw them, where they fit in the boiling point ranking system kind of comes in. Like, do they hydrogen bond or not? And then finally, are there any appropriate equations? But honestly, like with the alcohols, once you kind of get the scheme of how to name things, it's really just, well, what do you call it? Oh, you call it an alcohol. Okay, change the ending to OL, add a number. Done. You know what I mean? So it actually gets kind of easier for the next little while here. So let me start with this new group here. This is called a carbonyl group. And this is one that actually has to take up two bonding locations. So I was playing with the little stick things here the other day here. If I can kind of illustrate this one here, if you were to have like a nice carbon chain that has hydrogens everywhere, in order for this to work, you'd actually have to rip off two hydrogens. So like this hydrogen here would have to go, this hydrogen here would have to go, because what you do is you do a double bonded oxygen. Okay. And this causes a trigonal planar shape. You guys recall that terminology? Because what ends up happening is this goes in one, two, three directions, and then really these carbons, they keep going, and we don't know how far they go on either side, but this carbon then has a double bonded oxygen right there. Okay. One thought about this particular lone pair, it will definitely contribute to something being polar. However, it will not contribute to something having a hydrogen bond because this oxygen right here itself is not attached to a hydrogen. It's very similar to hydroxide, or not hydroxide, hydroxyl, the OH group we learned yesterday. The OH group from yesterday has this sort of shape to it. So it has that same sort of like three-directional kind of bend, I guess. This one's really trigonal planar, this one's bent. But this one has lone pairs and a hydrogen. This one right here just has lone pairs. So it's called a carbonyl. Now, depending on where the carbonyl is located, depends on how you name this thing. Okay. Sometimes the carbonyl is in the middle of a function, like in the middle of a big chain. Sometimes it's at the end, and sometimes it is combined with other things. So I'm going to show you the three options. Only one of them is actually on your diploma, by the way, so don't like overly stress on this. So depending on the location, here's how it works. If it looks like this, you have some carbons, you have that double bonded oxygen, and the carbon end caps with a hydrogen, you call it an aldehyde. So I'll try to draw you a couple here if you want to add some later here. This one would be like this: carbon, 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 double bond to oxygen, and stop. This is an aldehyde. Not on the diploma. Here's how you name it, though. All you have to do is change the ending to Al. So this would be prop and al. Not OL. OL is for alcohols. Al is for aldehydes, which makes sense, right? Aldehydes end with al. One more thing, there's no number required. The reason why there's no number required is that by definition, for it to be an aldehyde, it has to be on the end. And so it has to be on the end, then this would have to be the number 1. But why bother writing the number 1 if it has to be the number 1? So these ones are pretty easy to do. That's an aldehyde. A ketone is where you have the carbonyl in the middle of a group, and I kind of tried drawing one of those earlier. That's where you'd have like a whole bunch of these like this, and then on this one right here, you'd put the group. So it doesn't cap with a hydrogen to end it. This is a ketone. Here's how you name a ketone. You change the ending to -one. So aldehydes, the al is how it kind of works there. A ketone, the -one is the part we work with. So you're going to call this pent and -one. However, unlike the aldehyde, which is always like the last on a chain as to where you put it, this one right here can be anywhere in the middle. And due to that, you actually do need a number for this, because you could have put this one on this one here and made it a pentan 2-one. However, you could have put it on this one right here and made it a 3. If you put it off this one right here and make it a 1, it's no longer considered a ketone, it's now an aldehyde. Easy enough? Not on your diploma, not even on your test. I think I throw it on an assignment somewhere. But you could also call this 2-pentanone and just throw the 2 in front of the word. So the one I do need you guys to know is where this combines. This one right here is known as a carboxylic acid, and it combines multiple functional groups. What you end up having is your carbon goes up to this little functional group right here, the carbonyl group, but that exact same carbon also branches off to the hydroxyl group. Okay, this was possible for it to just cap with a hydrogen, keep going with carbon, but if it caps with the hydroxyl group we learned yesterday, this is called a carboxylic acid, and that is one that you do need to know how to say and how to name and stuff like that. So now, similar in concept to aldehydes, this has to be the end of a chain. There's no other way for this to work because this takes up 2 bonds, this takes up the 3rd bond. This can only continue on in one direction. That makes sense? And because of that, this would have to be on the number 1. So again, when we do carboxylic acids, there's no reason to number anything. We just have to know its naming scheme. So I've got a slide here on aldehydes that kind of goes through the concept. AL is the ending. Numbers are not typically required because it's always on the first one, not on the diploma. Ketones are next. Change it to ONE. Do include a number, also not on the diploma. Sorry, I'm like ripping through this because hopefully that makes sense. So here's the one we do need to focus on though, carboxylic acids. Carboxylic acids, we will often write it like this, COOH, which some people wonder, well, why don't we write it as like CO2H, right? Or why don't we write the, because like this does continue on with other stuff, why don't we merge it together? But the idea behind writing in this in orientation is to let you know that it goes C up to O over to other O to H, right? It's really meant to show you that. And you guys should be familiar with this in one compound we use, acetic acid. You guys remember what acetic acid is? It's CH3COOH. You guys have worked with this compound before at some point, I'm sure. Now this maybe makes some more sense why we write it the way it does, because this means you need a CH3, then a C up to O, although is it really up? No, it's just that's the way we draw it. Up to O, over to O, over to H like that. So this has the carbonyl group and the hydroxyl group attached together. So do you need a number for this? No, because I guarantee you it has to be on like the capped one right here. So here's how you name these things. No, I don't apparently have it listed on here. Let's talk about, before I get to the naming bit here, the properties of it. These things are usually either liquids or solids. Let's talk why. First of all, it's highly polar. The end that you're throwing on here is not even remotely symmetrical anymore, right? What you just did is you had a large chain of carbons, and now you have this O and this OH on the end. That's not at all symmetrical, right? This side over here is clearly lopsided compared to this one. So right off the bat, it definitely has dipole force, probably a considerable amount of it. And secondly, it can hydrogen bond. And not only can it hydrogen bond, it can actually hydrogen bond due to multiple locations. What does it take for hydrogen bond again? Hydrogen attached to either oxygen, nitrogen, fluorine, or maybe chlorine. Do we have that? Yeah, this oxygen-hydrogen works. So this hydrogen right here is highly protic, basically. It's a proton. But what else do you need to make a hydrogen bond? You need to have a... But guess what? Not only do you have lone pairs on this oxygen right here, you also have lone pairs on that oxygen over there. So when a second one of these molecules wants to be attracted to it, it has a lot of choice. This proton right here could be attracted to any of those 8 electrons that are kicking around there. So not only is it highly polar, it's also highly hydrogen bonding. Does that make sense? So this pretty much drops right to the top of our rankings in terms of boiling points. So yeah, very polar. And I don't know whether I have it written on here, but yeah, they have hydrogen bonds. Okay. Okay, so let's talk about how to name these things. Although almost everything has like a formal name, like say acetic acid, Actually, can I go back? Just keep on the slide you're on. Remember the one I drew right here, which was acetic acid? Where was that? Here it was. This was acetic acid. Although it has like a common name, the way we should have named it would have been to call it ethanoic acid. The way it works is that the F refers to how many carbons you have. See how there's one carbon here plus the extra one right here, F meaning 2. And then the way you name it is you just add anoic acid to the end. And that's how you have its like formal name. This one just has an alternate name, acetic acid. And almost everything has like a second or third or fourth name you need to sometimes just know. So if I were to go to this slide right here that we're on, this guy here is known as methanoic acid because literally there is just the one carbon. One is meth, right? So double bond to oxygen over to OH, and this carbon right here just stops. It doesn't even go any further. It just has a hydrogen. If I were to draw out some more, if I were to do like 1, 2, 3, then to this would be propanoic acid, butanoic acid, pentanoic acid, and so on. You could even go 2-methyl pentanoic acid. Well, you still need to have the longest chain you can have in a row. So this carbon right here has to be on your chain because it's a very key carbon. So how many in a row can you find? 1, 2, 3, 4, 5. And then see how this is now like a branch. And based on numbering schemes, we don't normally need a number when we talk about the pentanoic acid by itself, because I guarantee you this carbon right here is number 1, but then this one's number 2. There's a branch off of number 2. So, does that make sense? Okay, let's try a couple examples here. I'll just make a few up. So just find a random slide to kind of put some work on. So I'll make that one number 1. Make that one number 2. Make that one number 3. Why don't you guys try to name these ones? And honestly, only one of them's even on your diploma. All you really need to do is just know is what the rules are. So I actually just grabbed my my old organic chemistry textbook from university. If you guys would like, by the way, when you're doing one of the questions we have to look up functional groups, I actually have sticky noted a page of functional groups, and there's a ton of them in here. And literally what it does, you guys won't see it from here, but it gives you a picture of what the functional group is, and then at the end of it, it just tells you how to change the name. And that's really all you need to know is like, well, if you see one of these, what is the ending? Is the ending OL, AL, ANE, YNE, AMIDE, NITRILE, right? Like all you got to do is just learn what the suffixes are, and that's all it takes. And then a number, obviously, right? If a number is necessary. So first thing you're going to want to do then is recognize, like, I should give you another second here, actually. Still looking. Okay, so first thing you got to do is recognize what type of functional group you're being given. So this one up here, the double bonded O, you just got to figure out whether it's the ketone, the aldehyde, or the carboxylic acid. If it's in the middle, it's a ketone. So there's 3 in a row, so call it propanone. And you just got to figure out what number it's going to be. However, does this one actually need a number? No. Because on prop, if you tried putting this here, it wouldn't be a ketone, it would actually be an aldehyde. And if you put it here, same thing. So there's really only one spot this could be. So you actually would just call it propanone. You wouldn't even need a number. Oh, wait, this one right here has the carboxylic acid group where it has both the OH and the carbonyl group there. So you just got to figure out how many in a row you have. You've got 1, 2, 3, 4 in a row. So this will be butanoic acid. No numbers required. We're going to work with this stuff on Monday in our lab. We're going to do a lab where we're going to make different smelling compounds. Probably smelled my work before in the past. This one right here is actually disgusting in terms of how it smells. It's got a common name. It's actually known as butyric acid, B-U-T-Y-R-I-C acid. And this is really what's frustrating for me is that I have to like go to Wikipedia all the time and go, okay, what other common names does it have? So I would not expect you guys to know that without doing a Google search first. Okay, last one. This one right here, you'd have to find out how many in a row you have. So, I mean, like, for example, this could be your 5 in a row. Or it really is no different if you do, like, those as your 5 in a row. But either in a way, you've got 5. So it's a pent. And then since this is on the end of a chain, that's known as an aldehyde. So it's pent and al. Is a number required for aldehydes? There should really be no reasons why, at least for this bit. So it's just pentanal. And then depending on which way you approach this, I mean, this is 1, that's 2, that's 3. Off of there, you've got an ethyl, so it's a 3-ethyl. Pentanal. Sound good? Cool. Like I said, once you guys get the scheme of things, I bet you I could throw you my organic chemistry textbook there, show you new random functional groups, and as long as I tell you how to end the name of the word, you've got it. Right? So that's what I like about this part of organic, is that it's pretty straightforward. Okay, here's a slide where I've got a couple of examples of carboxylic acids that actually have more than one of the functional groups on there. You would not be expected to name these because, again, these guys have just been given common names. Like, for example, this one's oxalic acid. It actually has, like, a carbon with its carboxylic acid on one end, and same thing right here. It's almost like it's capped on both sides. Really, we probably wouldn't draw it like this. You'd probably draw it like this. One would go up like that, and one would go maybe down like this. Can you kind of visualize, though, how both sides of the molecule have been, like, capped off? This one right here is kind of cool. This one you guys probably will recognize, citric acid, right? Found in a lot of, like, lemons or, well, citric fruits, right? And it's got actually 1, 2, 3, 4, 5 carbons in a row. If you look at it carefully. This is actually a branch. That's a carboxylic acid. And it also has a hydroxide branch, or a hydroxyl branch. So, I mean, as it gets more and more complicated, we don't really have a naming scheme we would use. So, what I do need you guys to be able to do is this. I need you to recognize that multiple hydrogen bonds become possible. And so because of that, it increases the boiling point and melting point. So, like, I would expect citric acid to be maybe more of a liquid, which kind of makes sense because isn't that what we would notice in like fruit? Anyone want breakfast? Speaking of fruit, you could have some citric acid right now. Or not. Okay. Thanks, Marley. Okay. Here's my slide talking about how to name carboxylic acids. All you do is you drop the E off the end of the word and just call it an oic acid. So meth and oic acid. Pentan oic acid. That's it. It's super easy. We good? Cool. That used to be one lesson. Then I decided, hey, let's merge it together with another one. So, I guess we should do the example here. What's propanoic acid going to look like? 1, 2, 3 for the prop. Done. If they asked you like how many carbons and hydrogens there are, I would say that there are 3 carbons. There are 2 oxygens. How many hydrogens though? Yeah, this carbon right here is full up. You need 2 hydrogens here and 3 there, so 5 here plus that one for 6. So I guess that would be how you'd write it. But like no one would ever write it like this because that's not useful. You'd probably write it as CH3, CH2, COOA. That's probably the way you'd see it, just because it helps give you like some knowledge as to what it looks like. So say that again. Right. Yeah, like the way this guy works, if you zoom in here, is it's carbon to oxygen to hydrogen, and there's lone pairs on that oxygen there. Yeah. Yeah, this thing really, like you said, that's a unit basically. It doesn't get separated until I go to my next topic, actually. So, okay. What would we name this guy here? One, two, three, four. Bute and oic acid. I feel like you guys probably have this though, right? Okay, so funny that you mentioned that idea of that being a unit. Well, it is until you chemically react it with something, right? And so what I want to show you guys next is what we're going to do in our lab on Monday. What if you take something like a carboxylic acid and an alcohol and combine them together? So I mean, you guys can probably just see this in the picture here. Here's a carboxylic acid. If I were to name it, this would have been 2 in a row. So this would be ethanoic acid. 1, 2 in a row. And this guy right here, being an alcohol, just has the single carbon. So this would be methanol. So far, so good? Well, what happens if you start combining these things together? One of the really nifty things is that this guy's got an OH group, and this guy also has an OH group. And what we can do is we can take one H off of this guy and the OH group off of this guy and basically like rip out water. And we've already discussed this concept in previous examples. It is known as dehydration when you remove a water like this. We actually have a new definition for it. I've got a new terminology for it on the next slide here. We actually call it condensation, which kind of makes sense because condensation in like, I don't know, other places, condensation is like where it forms water and it rains. So this kind of makes sense as well. This is going to be a water forming reaction. You're going to condense out of water. And what ends up happening is this carbon right here and this oxygen right here, they like piece together. It's almost like you have a Lego piece here and a Lego piece here. You rip a piece off this one, you rip a piece off this one, and you slot them together, and you make this like hybrid molecule. And that's where we're getting to next. This is known as an ester. The way an ester works then is that there's some carbons on this side over here that come from carboxylic acids, and there are some carbons on this side here that come from alcohols. And what's unique about it is that the middle has an oxygen link. Where it doesn't go carbon, 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 it goes carbon, 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 oxygen link, carbon, carbon, carbon. And there's like a break in the middle of the molecule for an oxygen, which is kind of cool. You kind of visualize how that works? So take this top one right here. Come on board. Take this top one right here. It's got a 2 in a row group. That goes right here. Take this one, it's got a 1 in a row group, it goes right here. This stuff gets ripped out of the middle, so this group still sits there, and this one right here basically goes and attaches itself over there. That's called an ester. Esters are known for their smells, actually, so we're going to do this on Monday. We're going to basically take some carboxylic acids and some alcohols, we're going to react them together, and we're going to get a whole bunch of really cool and unique smells. One of the downsides is that one of the reactants we use, though, is butanoic acid, and as a reactant, it stinks. However, once it turns into a product, it actually smells nice. But the downside is that like the reactant that you start with is so pungent in terms of its odor that sometimes it's overwhelming. So hopefully under the fume hood it'll be okay. Here, I actually want to go find this slide right here if you guys want to skip ahead one. Here's a whole bunch of different smelling esters that we're going to try to make. We won't do them all because I don't have every compound. But like if you want to make apple smell, you need to make what's known as a methyl butanoate. Now, I haven't shown you how to name these yet, but hopefully this formula helps. What we're going to need is a 4 in a row group and a 1 group. What this means is that our acid must have been butanoic acid, and our alcohol, I want to take a stab. What alcohol would we use? Methanol. Good, good. You're on top of things. Okay. Let me try another one here. This guy right here needs a 2 in a row group. So the 2 in a row group means you better use ethanoic acid. And then this right here is 7 plus 1. So they've shortened it up, but that's 8 in a row. So 8 in a row means you better use octanol. And basically, this is super easy lab we're going to do. I'm basically going to give you a whole list of alcohols you can choose from, a whole list of carboxylic acids you can choose from, and you just react them together, let it cook for a little while. Like you have to let it like react for about 10-15 minutes, and then after it's done, it should create kind of an oily, waxy substance, which is an ester, and that ester should hopefully have whichever synthetic smell we're kind of working with. In theory, you could actually taste them, because I don't know that you guys know much about like taste and smell, but they're highly related. Like your taste actually kind of comes from smell sometimes. So the only downside is though is one, I have a rule we never eat things in the lab, and two, one of the byproducts of this, we have to use a catalyst of sulfuric acid, and I don't have a safe way of separating out the sulfuric acid, so we won't taste them, but we'll definitely smell them. Anyways, let me go back to the slide I skipped here. I have two different terms I need you guys to know for reaction types. The first one is known as a condensation reaction. Okay. Condensation is an overarching term for whenever you take a carboxylic acid and react it with something, and water is a byproduct. That's the real key here, is that water is a byproduct of condensation, where chemical A, which has like an OH group on it, and chemical B, which also has an OH group on it, when they react, a water can be ripped out of the molecule. That's known as condensation. As a subheading of condensation, if it specifically makes an ester, then we call it esterification. It's a fun word to say, esterification. So I'm going to show you guys some more condensation reactions later, because not every condensation reaction makes an ester. But do you guys follow how that works? Condensation means it produces water. Esterification is a very specific one, which produces an ester and water. Okay, let's talk about how to name these things. Here's how it works. I've got kind of this diagram with color. I don't know, yours probably aren't in color, but hopefully you can kind of follow this. This one is different because it has two words to it. Okay? Whenever you name esters, because of the fact that there's carbons on this side, then an oxygen link, and then carbons on this side, there's always two halves to the name. Okay, I'm going to actually start with this guy's name right here. See how we've got this oxygen as the middle linkage right here? You've got to figure out the two different sides. Right here is a side, and right here is a side. Okay, we always start with the branch side, which is the one that does not attach to both oxygens. You see how this carbon right here attaches to both oxygens? It's kind of like the main carbon. We're not starting with that. We're going to start with the branch. And so as a branch, there are 1, 2 carbons, hence we call it an ethyl. Then for the remaining bit, this carbon right here, the main carbon, the one that does attach to both oxygens, count up how many it has. It has 4 in a row, so that makes it a bute. And then the suffix for it is -ate. So this would have been butane. Call it butanoate, with a branch of an ethyl on the end. How do you make it then? Well, the O8 came from a butanoic acid, and the ethyl group came from an ethanol. So hypothetically, let's say you used methanol instead, which you guys can do in our lab the other day, where you're like, hey, let's just try this one. If you used methanol, all that would happen is you wouldn't have quite as much of that, and it just means that you wouldn't have that one there. And rather than calling it ethyl butanoate, you would have called it methyl butanoate. Or if you didn't have butanoic acid, but you had one where you could go one further, and you had pentanoic acid, then it would have been a pentanoate. So this one's a little bit trickier because it's not quite as straightforward of a naming scheme. You do need to know that it always ends in 08, and you need to know that it's always a two-word combo. The single hardest part I found students come across is they have to know which one is which. Is this the first part of the word and this the second part, or vice versa? So the key I want to point out is focus on this carbon right here. The carbon that's attached to both oxygens, it is the main part of the word, and then the carbons that are only attached to the one oxygen, that's your initial branch bit. So let's try another example here. Well, apparently I don't have more examples. Let's do this one here. Okay, so what we've got here is a butanoic acid, because it's got C3H7, but one more C. So there's actually four carbons here. And we've got a methanol, because there's just the one carbon. So when you put it together, you would call it a methyl butanoate, because the methanol made the group and the butanoate made the rest. Why don't I try drawing it out just to make sure you kind of visualize it? Butanoic acid should look like this. 1, 2, 3, 4 in a row. 1, 2, 3, 4, 5, 6, 7. This guy goes up like that and to there. There's your butanoic acid. Your methanol would look like this. I'm going to put the alcohol on this side over here. So there's our initial amounts. By the way, when you guys do our lab on Monday with this, it's going to be very similar to the one we just did, where all your analysis is going to be is just drawing out equations. What ends up happening is between the two hydroxyl groups right here, it really doesn't matter which one, but like one oxygen and two hydrogens get ripped out, and then the rest slides together. So when you're done, you're going to have 4 in a row. This one will go up to oxygen. But then this oxygen here slots in there, caps up with the carbon. How do you name it? You call this a methyl for the one right here. And then for this one right here, it's a butanoate. Except you'd, of course that didn't work. Except you put the name in the front. So this methyl actually goes first. Does this make sense? Can I go back a slide then, if you guys are okay with this? I want to talk about properties of this, which I think was on this slide right here. Esters, if we had to rank them, come below carboxylic acids. Is the reason why. Esters actually can't hydrogen bond. Take a closer look at what we just made here. This guy right here is the ester. Can it hydrogen bond? What's the requirement for hydrogen bond? You need lone pairs. By the way, there are lone pairs on both this oxygen and that oxygen. There's plenty of lone pairs. But do you have an oxygen to hydrogen combo? No. You have oxygens and hydrogens, but not to each other. So the most important distinction I need you to know is that this thing right here cannot hydrogen bond. So these guys right here are lower than alcohols and carboxylic acids. Carboxylic acids are like our best, because they can hydrogen bond and they have so many lone pairs. That's awesome. Alcohols are next, because they can hydrogen bond, but they're not quite as good because like it's almost like an upgraded alcohol is what a carboxylic acid is. Esters are probably next then. Esters are probably polar. They're probably not perfectly symmetrical, but yeah, they're not going to be able to hydrogen bond. Now, one of the things that does happen though is that sometimes they can become very large, which actually means they can become solid. The reason why they're so large is that you can have like 8 carbons on this side, then the O group in the middle, and then 7 carbons on this side right here. And so they can be quite large, which leads to polarity and London forces kind of taking back over again. But yeah, they can't hydrogen bond. So a lot of these things are actually naturally found. Some are synthetic. So when you like, for example, you use like say Febreze or like a car air freshener, you're probably smelling an ester. Does that make sense? Because, or another example here, let's say you go buy gum and you buy wintergreen, like winter fresh gum, you know, like that really pepperminty flavor type stuff. You're not actually eating ground up peppermint or ground up watermelon. You know what I mean? Like there's a synthetic chemical that has that flavor. Esters are that synthetic flavor. So like when you go back to a chart like this, when you guys have like gum and it's like, ooh, minty fresh, you're probably actually tasting wintergreen, which is methyl salicylate. And that's what you're actually tasting. You know what I mean? So yeah, there's a benzene ring in it. This is actually based off something called salicylic acid and methanol. And I actually have both of these. This one here, when kids make it, it usually smells like a lot of kids think it smells like root beer actually. So most kids usually like this lab. All right, let's move on here because I want to try to finish that second lesson if I can. What do I got left here? Let's see. This one here, we just need to name this or look at it, don't we? Draw a line structural formula equation and write the IUPAC. I missed a P there. Name for the ester. I think this gives it away though, because here's benzoic acid. Here's propanol. So the propanol becomes a propyl, and the benzoic acid becomes benzoate. I don't even know what I was going for here because the answer is right in front of you. Does this make sense to you guys? Can I move on? Okay, I almost forgot the most important thing though. I mentioned this though. This requires a catalyst, which is the single reason why I can't let you eat these. The catalyst is sulfuric acid. You should probably know that. I don't know that I've ever seen it tested, but it's a very common catalyst for this one, sulfuric acid. So yeah, I can't let you eat these on Monday. Sorry. Okay, why don't we work backwards? This is one where we can actually do a task. I'm gonna give you a chemical formula. We need to be able to do two things. I need you to be able to name what this thing was, and I need you to be able to tell me how to make it. What would have been required to make this? So the first thing we should do is figure out like how many carbons are on both sides. This is one side of your ester, and this is the other. Which one actually comes first? Yeah, it's actually the one on our right, because this guy here is the branch. So a group of two would actually have been known as an ethyl. And then for the main core, 1, 2, 3, 4, this is actually ethyl, bute, and noate. If I wanted to draw it out, it would have looked like this. There would have been 4 in a row. The last carbon goes up to oxygen, over to oxygen, and then branches off with 2 more. And so if I want to like color code it, this is your ethyl from right here. This is your bute right there. Is that pretty straightforward? Second question. Let's say that I tell you that ethyl butanoate has the best taste in the world you've ever had. It's bacon flavored. Because really, what's better than bacon? Maybe not, actually. Okay, so let's say though you want to make ethyl butanoate, right? That's your goal. What 2 reactants do you need to make ethyl butanoate? What alcohol do you need? Ethanol is your alcohol. And what's your carboxylic acid? That makes sense to everybody else. The ethanol gets you that. The butanoic acid gets you this. So Sound good? Cool. Okay. Got a summary slide. That's all I got. You guys want to do the next one? Just finish off the unit? I got half an hour left. I'm pretty confident I can do this. You guys okay with this? Okay, here, I got the notes already ready, so. Yeah, it's not that much, this last one. You guys need this one too? You have it. Here, just in case you need it. I know, yeah, color. Did I get everybody? Okay, esters are the last functional group you guys need to be able to do. So if you want kind of a running tally of the ones you need to know for your diploma, you need to know how to do the organic halides. You need to know how to do alcohols from yesterday. You need to know how to do carboxylic acids, and then esters. Those are the only four you have to be able to do. But I threw in aldehydes and ketones in there just because, and I think on your assignment I even throw in amines. Because honestly, like, hopefully you guys agree with me, like, all you got to do is just change the ending of the word. You just look it up in a book. So, by the way, I'll leave this out here for the foreseeable future. When you guys are looking to do questions on your assignment, this sticky note right here has some stuff for functional groups. And when I eventually ask you about making amines or amides, there's a sticky note in there on it. So I'll leave this out here if you guys ever want to look over my old organic textbook. Okay, here's my last topic then. One of the things I'm asking you guys to do for your research paper is to research some pretty cool synthetic compounds that have practical purposes. And one of the ones that you may end up doing involves some sort of polymer. Okay. The word poly, you guys have heard that prefix before. Poly means more than one. Okay. Sometimes what ends up happening in organic chemistry is that you end up having a repeated chain that just keeps going over and over again. You have one of these, and you have another one, and another one, and another one, and you can just keep replicating it over and over and over again. The example I give, if you need like a silly analogy, you guys know those like barrel of monkeys, where like the arms are like opposite ways so you can like hook them to each other? That's what I think of when I think of these polymers, where you have this individual compound, but then it hooks onto another one of itself, and it hooks onto another one of itself, and it hooks onto another one of itself, and I could keep doing this for forever, but that's how we get plastics. Because really what it is it's a self-replicating, well, that's where the name polymer comes from, right? Where just it keeps going and going and going. And these are really the foundation of so many of the compounds that we now use that we just kind of probably take for granted. So the terminology I need you guys to know is the word polymer and monomer. If you like my barrel of monkeys example, a monomer is a single monkey. But a polymer is where the monkeys just start linking arms and basically forming one big long chain. Right? So large molecules made together by, keyword here, linking together the smaller ones. And so I'm going to show you guys today 2 quick ways that you can make some polymers. This is not by any means the entire list, but the 2 ways are either known as the addition or condensation ways. And we just talked about condensation a little while ago, so we'll come back to that in the polymers here. Let me show you basically the concept behind how addition polymerization works. Imagine you took this molecule right here. This would have been propene. The reason why it's propene is that there is 1, 2, 3 in a row. See how it's kind of bent around the corner? It's kind of meant to throw you off, but you bend this around the corner. This is propene. And what we're going to do is we're going to take multiple propenes. And so I'm going to draw this out here. I'm going to do a C like this. And this would be known as my monomer, where I just have one of them. And then if I select this, and I copy it, and I paste it, and I put another one right here, and I paste another one and put that right here, and maybe just one more, and I'll put it right over kind of there. Here's what ends up happening, is the electrons just do a quick little shift. Because right now, they're not actually attached. You know what I'm saying? Like, all of these things are actually not in a row. But if we break this double bond and put one there, and break this double bond and put it there, break this double bond and put it there, All of a sudden now my barrel of monkeys that was all separate, now their arms are linked. And now you have a polymer. And could you repeat this? Yeah. You just keep going, right? Add another monkey to the other side and make this just a longer and longer chain. And because of that, we don't really want to count them up anymore because that would be ridiculous. Because you might have like 47 trillion of these things kind of just continually going for forever, right? So what we do is when we name it, we call it poly, and then we name it based on what we originally started with. And so this molecule right here was propene, so we call this polypropene. It's actually been abbreviated to polypropylene, and you guys might have heard of that before because polypropylene is like a basic form of plastic. Anybody ever heard of that one before? Polypropylene? Polyethylene, polystyrene, anything that starts with the word poly, the second half of the word lets you know what you were repeating over and over again. So the way we do that then is as a shorthand method, what we do is we write a little bracket around this and we write N down in the corner. N meaning that like this individual thing just keeps repeating over and over and over again. So I think I have better pictures later on here. Yeah, here's a good one. Here's your propene, right? You've got this one and this one and this one. And what eventually ends up happening is you bust up all these double bonds, and like really this bond shifts to here, this bond shifts to here, this bond shifts to there, and all of a sudden you've made a long continuous string of this stuff known as the polymer. And so if this started with propene, like I just said, you now call it polypropene. But it probably has been given a formal name somewhere along the way, so you call it something else. But this is its like technical name. And then rather than writing this over and over again, put it in brackets, put an N next to it. So, does that make sense? Here's a couple more then. I'll do the bottom one here. This is polyvinyl chloride. I mentioned this one before. Polyvinyl chloride is PVC piping, which would be just your generic really hard plastic, right? So how do you make it? Well, you have to start with a vinyl chloride. A vinyl chloride is the common name for two carbons with a chlorine. And this is really important though. For it to be addition, you have to have double bonds. That's so important. I'm going to say it again. For it to be addition, it has to have double bonds. Because really all you do is you take this double bonded molecule and the same one and the same one. And again, this is just like your monkeys, right? And this double bond busts up. This double bond busts, this one busts up. And instead you just put a link in between, which is why I think my barrel of monkeys analogy fits, doesn't it, right? Because all of a sudden you now link their arms together, and this bond now goes here, this one goes there, and all of a sudden you have this repeating unit, polyvinyl chloride. Or this one right here, this is just your basic ethene, just two carbons right next to each other, right? Same concept, bust up all the bonds, link them together, polyethene put together becomes polyethene. It almost always has to end in an ene, because in order for it to work, you had to start with something that was double bonded. I don't know. Probably. That's one of the cool things about these polymers is that like there's so many that just get discovered and made, right? So yeah, you might be able to. I don't know of one right now, but okay, you guys will probably recognize some of these symbols right here. Almost everything that is a poly something polymer has a recycling code on it. You guys ever seen these on the bottom of your like plastic bottles and stuff where there's like a 1 or a 4 or a 5, right? Those are actually codes for what type of plastic it is, so that when it eventually gets recycled, it goes into the right sorting bin, right? Now, I mean, at least if I don't know for me in Lethbridge, they just have one big bin for all the plastics to go into. So if it's plastic, it just goes in the big bin, right? But you get what I mean, right? Like eventually it's going to get sorted into polyethylene terephthalate, or into polyvinyl chloride, or polystyrene, or polypropylene, right? And so they just have a different code on them. But you guys have probably seen this before, right? Okay, moving on. Here's another really cool one. This one's Teflon. Teflon is basically carbon-carbon with fluorines everywhere. It's actually tetrafluoroethene. You have 4 fluorines on an ethene. And if you basically smush all of these ones together, you get polytetrafluoroethene. But you guys can kind of see that like some of these names get a little ridiculous over time. So rather than calling it polytetrafluoroethene, we just call it Teflon. So, cool. Here's a few more if you want kind of some examples. My favorite one, by the way, is talking to people about how PVC and saran wrap are so similar to each other. This one's polyvinyl chloride, your basic solid piping. 2 carbons, 1, 2, 3 hydrogens, and a chlorine. Okay, now compare that to saran wrap. You guys know saran wrap. It's like thin and flexible and very pliable, right? The only difference, change this chlorine from a hydrogen. That's it. That one subtle little tweak. And all of a sudden, rather than being hard and rigid, now it has like that, I don't know, flexible tendency where it's useful for food storage, right? And that's what I love about chemistry is that people then just try this extra little tweak. Well, what if I do this? Oh, cool. I made something useful, right? A lot of chemistry, actually, a lot of innovations are sometimes made by mistake. For example, a common one, you guys know sticky notes. How there's like that adhesive that's the very, very top part of the sticky note, so it barely sticks to stuff. Apparently, the rumor is, I gotta look into this one, that was actually a mistake that I want to think it was NASA. They were trying to develop some sort of really awesome adhesive. Someone nodded. Anyone heard this one before? I tell you the story? Yeah. NASA or someone like that was trying to make a super really good adhesive, and they ended up making one that was actually like just kind of good. It's not really sticky, but it lasts for forever, right? You can like repost a sticky note like 10 years later. So, and yeah, it just ends up probably being some sort of polymer where they just made a subtle tweak to it. So, all right, anyways, let's move on here because I'm getting close to the end of the class. That's one type of polymerization you should know, okay? And you should be able to name it. So it's super straightforward. Find me the monomer and just put it poly that. So if you were working with a styrene, call it polystyrene. If you're working with an ethene, call it polyethene. Okay, that's all you have to be able to do. The second one I need you to know, we don't actually name, but you should be able to recognize it. It's called a condensation polymer. And we just talked a minute ago about how we can take 2 compounds that were separate, an alcohol and a carboxylic acid, and we could merge them by ripping a water out of the middle. Right? Because isn't that what an ester did? We took compound A and compound B, we put them together, but for them to link, it's like you had to rip this one off, rip this one off, and then they stick. Right? Well, that same logic can then be applied to esters. Hence the name polyester. That makes sense? What do we use polyester in? Yeah, it's mostly used in clothing, right? And so the clothing you're wearing is actually from the petrochemical industry to some degree, right? So otherwise we'd be wearing either like cotton or wool, something along those lines. So, okay, here's the most important here. Each part of the monomer that forms this polymer must have 2 functional groups, one on each end. Okay, I need you guys to be able to have good spatial visual skills here. So once you're done highlighting this, you have molecule A and molecule B, you want them to stick together. So right now I need my thumbs to basically link. And for that to work, I need to have a functional group here and a functional group here, where I rip the H and the OH off so they can stick together. But now I've only stuck 2 things together. I then need this finger over here and the following one to also be able to stick, and those ones to stick, and those ones to stick. You get what I'm saying? So you must have double-sided molecules. You would want to have something that looks like this. A couple of carbons, and then you want like an OOH, so that an OH on this side can eventually stick together. But this side over here also needs to have the exact same thing, so that another one over here like this can rip out, and that can stick together. So addition's a little bit different than condensation. Condensation actually has a pattern. It always goes A, B, A, B, A, B, whereas this would have been an ester, but it needs to then link up to the one on the other side of it. And this one needs to link up to that one, to that one, to that one. So it doesn't actually have one unit that repeats. Polyesters that come from like condensation reactions have like alternating units that repeat. You guys get the difference there? So a visual is going to help, I think, on my next slides. This one right here, I'm not great at my biology. You guys talk about dipeptides in biology at some point before? Some of you, okay, good, you're nodding. I have no idea what they do, but I can tell you how you make them. Cool. Here's how you make one. You take a glycine and an alanine. This is your glycine, this is your alanine. And here's what ends up happening. This OH group right here and this H right here, they end up basically falling out. And then this carbon right here links up with this nitrogen right here. So what ends up happening is it goes carbon up to oxygen, down to nitrogen to hydrogen, and that's what happens right here. However, you could keep doing this over and over and over again. Because imagine that I took another one of these molecules right here, and I re-put it over here. I put another H to N to H to CH, right? See how I could do that again and rip it out right there? And I could take the same molecule and put it over here. I'll just draw the back half of it. Here's the back half as well. So that would be like this back half right here. And I can do the exact same thing. You must have double-sided molecules where you have a functional group on both sides, because otherwise you just stick two of them together and it would stop. You have to have both ends be able to continually repeat. So that's actually how you make a dipeptide. Okay. I've got some notes in here. You guys can probably just read through these because I don't have a whole lot to add. But like our lipids and our fats sometimes work together like this, where they get built up by adding carboxylic acid through esterification reactions. Why don't I skip ahead? Like nylon also works this way. Quick little look here. Nylon, the way it works is that you have this OH and this H right here. They can fall out. And then if I rewrote this molecule over here on this side right here, if I rewrote the exact same one on the other side right here, hopefully you can see how this could come out. But like it has to have an A, B, A, B. Like it has to have a repeating pattern to it for it to link. Good news for these, I don't need you to name any condensation reactions. All I need you to be able to do is recognize them. If you can see that it's happening and just recognize that, that's all I need you to do. So be able to name an addition polymer, be able to recognize condensation. Here's how polyester works. Polyester works with carboxylic acids and alcohols. And again, you rip that water out of the middle. It just means that you have to have a double-sided carboxylic acid. So you actually have to have a dicarboxylic acid and a dialcohol. Because otherwise, if you just put this one together with this one here, they'd stick together and then you'd be done. Right? So, and your clothes don't smell like esters, right? Well, that'd be cool. Scratch and sniff. Raspberry. Anyways. Okay, so here's here's how this might look. You'd have a dicarboxylic acid where you'd have carbon to carbon, OOH like this. I don't care how many things you have in the middle. You'd also have to have a dialcohol where you have an alcohol on both sides. And again, I don't care how many carbons you have in the middle. And then basically what ends up happening is A links up to B, which links back up to A, which links up to B, which links up to A, which links up to B, and you just keep doing that for forever. Right? Hence polyester. Really cool, eh? This is one of the reasons why I think you need to do your research paper, is that, like, there are some pretty cool compounds that have fundamentally changed our world, right? We would be wearing cotton and wool. But, I mean, now we can make, like, I don't know, all the different clothing. And, I mean, not only just think the clothing, but, like, how it affects things like, say, like sports performance, right? All of a sudden, now the uniforms that you wear are, like, form-fitting. So all of a sudden, if you're a track athlete, now it shaves seconds off your time. Or swimmers, for example, the swimsuits that they wear in the Olympics now, like they have like almost probably no friction on them at all, right? They are streamlined as much as possible. Go back 100 years, and you were wearing probably something that was gonna like absorb water, right? And so you'd get weighed down as you're trying to swim. So, anyways, you guys get my point. I think that's it, right? Cool, guys. We finished organic chemistry. Okay, I really did try to rush a little bit there. Do you guys have questions for me? I do an okay job still at explaining things? Okay, let me do a quick summary then of what we covered today while you're packing up. In our first unit, I needed to show you guys more functional groups and an equation type. The only functional group you really care about is the carboxylic acid. So to name it, figure out how many carbons you have in a row and call it that oic acid. So butanoic acid, pentanoic acid, something like that. Okay. Then we talked about how to combine it with an alcohol to make an ester. The hardest part of that is just to figure out which part of the word goes first. You've got a branch part of it and you've got a main part of it. The main part is the carbon that has both oxygens. The branch is the one that only has the one oxygen attached to it. And you just call it like a methyl propanoate or a butyl ethanoate. Okay. We'll do our lab on this to help kind of give you some practice. And then the last thing we talked about was the polymers, two types of polymers, addition polymerization and condensation. Addition must include double bonds. And you basically take the same double bonded molecule over and over and over again, smush them all together, break the double bonds, and call it a poly something ene. It's going to end in ene, probably. I guess now that I think about it, polyvinyl chloride doesn't actually apply, but yeah, it probably ends in ene, like polystyrene, polyethylene, polypropylene. The second one is the condensation reaction, where you need to have this one and this one linked to each other, and water comes out of the middle. The key there is it has to be double-sided. In terms of naming them, don't worry about naming anything that is a condensation reaction. They all have common names anyways. But you should be able to name the addition ones. That was our day. Sound good? Cool. Okay, you guys should be able to start working on that assignment now too, by the way, because now that I've covered everything, that works. So I'll leave my organic chemistry textbook out there. You guys will find it useful for at least 2 of the questions. So other than that, I guess you guys can do what you want for the last 10 minutes.